Alright, so for the remaining types of problems that we've got, we're going to be given some function. That function is going to equal an integral idea. That integral is going to be defined on an interval. Normally it's going to be starting with a constant. In fact, it will be starting with a constant. And it's going to range up to variable x. Because after all, we're going to start with a function here that is in terms of x. Now what that integral gets applied to, it's going to get applied to another function that's in terms of another variable. Kind of like the t stuff we talked about from last time. So our function here, got the square root of 2t squared minus 3. Got our dt at the end to make this official. If this is the given information on this type of problem, we're going to be asked to find three things. First thing you're going to be asked to find. You're going to be asked to find the value you get when you take, on this one, 3 and plug in. So go back to the function that's given, understanding that 3 is going to replace the x in the original function. Notice the only x we have is right up here at the top of the integral. So if we plug that in, wrote it all out, we'd have our integral, got the 3 at the bottom, now we're plugging in the 3 at the top. All of this is applied to this function. Got the dt at the end. Obviously the question becomes, what does that all equal? Any guesses?
Wouldn't you just plug in 0?
There you go.
Oh, yeah.
It equals 0. Because think about what this definite integral is supposed to mean. You're finding the exact area beneath the curve of this function, right? And it's on the interval from this number to this number, which happens to be the same. You're not going anywhere, so what's the area going to be? Absolutely nothing. So your answer is 0. If these numbers are the same, we get 0 over here. And if you have the question right now, is that supposed to happen on all these problems? Yes, that's supposed to happen on all these problems initially. These two numbers should match. Well, it's always going to be 0 unless they throw something at you where, you know, over here with this function, we've got something else added on. And then, of course, whatever you get here with that 0, you'd have to add that on, but that's not too hard to fix. Now, next step you're going to notice is a little more consistent with this second fundamental theorem idea. For the next step, we're going to find f prime of 3. We're going to find f prime. That means we're going to have to take the derivative of the original function. So going back to the original function here, taking the derivative of that function, do a little work down here, just finding f prime of x right now. That means I would have to apply this derivative idea, so I'll introduce the d dx again, to the other side. So the other side was that integral. There's my work showing that, hey, I'm applying the derivative to both sides. So with the second fundamental theorem, we're supposed to appreciate that if we see this little d dx in front of some definite integral, we just go through, we basically apply that formula that is the second fundamental theorem. And to do that, we start by taking this top value here, plugging into the function here for t, getting the square root of be 2x squared minus 3. As the rule continues, you're multiplying on the derivative of that x you just plugged in, right? So you're multiplying on a 1. Then you're subtracting. We go down to this bottom value, plug that in for t. You've got the square root of, if you spell it all out, 3 squared minus 3. Take the derivative of that 3, that's 0. You tack it onto the end. But if you've done enough of these problems, should recognize what's supposed to happen in the first place, right? Whenever we're plugging in these constant values down here, we're getting these zeros at the end, which cancels out this second piece. And if all we're plugging in initially is an x, knowing that derivative is 1 right here, that's canceling itself out as well because we're just multiplying onto the square root of 2x squared minus 3. In other words, you're taking the derivative of an antiderivative, you're going to get this function back. All we're doing is replacing the variable. So f prime of x is this guy. We need to find f prime of 3. So just take 3 and plug in. You've got the square root of, be 2 times 3 squared minus 3, squeezing this in. So what does that come out to be? That comes out to be the square root of 15, right? So on these 3-part problems, basically you get to part B. Part B is going to be where you're applying the second fundamental theorem. It's where we apply our new stuff. Now that we know that f prime of x is the square root of, what was it again? 2x squared minus 3. Let's keep that in mind as we do this last part. For part 3 on these problems, you're going to look at a second derivative of the original function that's given. So f double prime, and ultimately your goal is to evaluate f double prime at 3. So we're plugging the same number every time, just taking derivatives as we go. If you need to find f double prime, let's start down here again, find f double prime of x. What do? Well, this is the first derivative, right? To get to the second derivative, what do you do with the first derivative? Take the derivative, right? So I'm going to take the derivative of this guy. If I write this out, kind of like I did on the last problem, showing that I'm applying the derivative now to what I had up here for the first. We've got 2x squared minus 3 as a quantity raised to the 1/2 power, right? Nice to know, because if you're going to take the derivative, we got to bring down that power 1/2. We got to keep all the stuff inside the same. Got to subtract 1 away from that power. And then what? Yep, tack on a 4x, because that's the derivative of the inside. This is our chain rule. Back in the good old days where we just took derivatives, we left that as is, but now that we have further applications where we need to plug in a number, like 3, we should simplify this a little bit. Now, we've done this a lot in the past too. You've got a negative exponent. So we know that with the negative exponent, we're dropping that stuff down to the bottom. Okay. You could.
Okay.
If we're going for an exact value, though, you know, it'd be nice to clean this up a little bit. So we're bumping the negative exponent down. That becomes a positive 1/2. Ultimately, we're taking the square root there. Denominator of 2, throw down there. Anything else would stay on top, so you got anything else 1 and 4x. If you're asking yourself, can you do something with the 4 and the 2? Sure. Don't know why you're talking to yourself, but you can. If you cancel those out, you've got a 2x now left on top. So f double prime of x is 2x over the square root of 2x squared minus 3. We're trying to find f double prime of 3. So take 3, plug in for your x's. If you plug in for your x's, you've got 2 times 3 on top over square root of 2 times 3 squared minus 3. There's that square root of 15 again. And on top we've got 6. And I don't mind if we're leaving radicals on the bottom. We've done enough work as it is. There's your answer.